We now come to the important part of the course, which is the stationary action principle. So let me first define what is an action. The action is defined as the time integral of the Lagrangian, which is itself a function of the path which connects two specific events. Of course, there are many paths connecting these two events, and each of them is expected to give a different value for the action. What we want is to find the classical path, that is the path which obeys Newtonian mechanics. First, we would like to see if there is something special about the path which leaves the action stationary. So we are looking for the stationary path, such that small variations around this path doesn't change the action in first order of these variations. Here epsilon is a small real number and n of t is an arbitrary function with the condition that when evaluated at t1 and t2 it has to be 0. The reason for that is because the initial and final events are fixed. We are looking for variations around the stationary path, but we should not touch at the initial and final events. Calculating variations of functionals is quite complicated and advanced. However, what makes the problem simple here is that epsilon is just a number. So, of course, s is a functional of the path, but it's a function of epsilon, because epsilon, as I said, is just a number. Therefore, we can use standard Taylor expansion and derivative for functions. So we see that to have x0 a stationary path, what we need is to have the first derivative of s according to epsilon equal to 0. So let's calculate this derivative. Okay, so we see that we get a result where we have both n and its time derivative n dot. The problem is that n is an arbitrary function. So therefore, we have no idea how to take its time derivative. So we need to find a way to factorize n, or to get rid at least of this time derivative. And for that, we are going to use one of the most common tricks in physics, which you will see again and again if you take further courses in physics. And this trick is integration by part. So we have already seen integration by part earlier in a video. So if you don't remember how it works, I encourage you to watch this video again. I'm going to apply it here just to factorize n. In this last term, we use a notation where we take the difference of what is between the bracket between t2 and t1. But we already saw that the function n is 0 at t1 and t2. Therefore, this last term is simply 0. Now, looking at the first term, we see that it's a product of the arbitrary function n with what is between the bracket. But because n is arbitrary, it's not 0 we can choose it not to be 0. Therefore, if we want the first derivative of s according to epsilon to be 0, the only possibility is for what is between the bracket to be 0. We recognize the Euler-Lagrange equation. Therefore, the classical path, which is a solution of the Euler-Lagrange equation, is the path x0 which leaves the action stationary. So we just showed that the stationary action principle leads naturally to the Euler-Lagrange equation, and therefore they are equivalent. Remember also that we showed before that the Euler-Lagrange equation and Newton's second law were also equivalent. Therefore, all these three postulates or principles are the same thing. Stationary reaction principle equal Euler-Lagrange equations equals Newton dynamics.